Okay, so let's continue on what we have learned. Okay, so it's about temperature and heat. Okay, it's about temperature and heat. In this chapter, okay, we have learned about temperature and the zeroth law of the thermodynamics, which include how we will learn about scales in temperature. So for example, okay, we have learned about the zeroth law of the thermodynamics, okay, including the definitions of heat. Okay, that means heat is energy. Okay, some terms, okay, that involved in the temperature and heat, which is thermal contact and also thermal equilibrium. Okay, so it brought you to the temperature scales, which we learned about Celsius scale, Fahrenheit scale. Okay, and then how can we convert between Celsius to Fahrenheit, and then Fahrenheit to Celsius, and then we will learn about Kelvin scale. Okay, that comes from the absolute zero here. Okay, the Kelvin scale is always related to a Celsius scale. So the main point here, if you want to convert it to Kelvin from Fahrenheit, you must go to Celsius, and then from the Celsius you can convert to Kelvin. Okay, okay, so we can also see that if you want to convert it to from Kelvin to Fahrenheit, okay, you must come to Celsius, and from Celsius you need to convert it to Fahrenheit. Okay, so basically these are the three temperature scales. If we do some comparison between them, so the Celsius is like more like the very small value. Okay, it comes in the smaller value compared to Fahrenheit and Kelvin. Okay, right. So we also learned about we do some recap on the thermal expansion. Okay, about the linear, about the area expansion, and also about the volume expansion. Okay, and then we have discussed a little bit in terms of heat and the mechanical work, which involve some after all this while we learn energy in terms of joule, but instead of joule we can also state the unit of energy in calorie. Okay, kilocalorie, for instance. Okay, kilocalorie, and also British thermal unit, BTU. Okay, so we have done some calculations in terms of calorie, right? So these are the examples. This is one of the examples involving energy in terms of kilocalorie. Okay, so now we come to the specific heats. Okay, so let me do a little bit of definitions of the specific heats. Okay, so what is specific heat? Okay, so in the specific heat, okay, we must know the terms of heat capacity. Okay, heat capacity. In this case, heat capacity is the energy that energy required to increase a temperature. Okay, energy required to increase some temperature of some substance. Okay, in this case, equals to Q over T. Q C equals to Q over T. Q is energy. Delta T here is the change in temperature. Okay, but the specific heat capacity, this is just heat capacity, but when involved specific heat capacity, okay, we have a look at how important is the mass when it comes to the specific heat. So we need to add another mass. Okay, we need to add M to this equation so that it will become like this. Because, okay, look at this argument. Okay, if we take water, Okay, for example, since it takes about 4,186 joule to increase the temperature of 1 kilogram of water by 1 degree Celsius. Okay, so it happens that if we add some more water, okay, if we double up the water, let's say 2 kilogram of water, it will take uh, twice the value of the energy. Okay, we need to add twice. Okay, if you increase this one by 2. So with these things, okay, we need to add mass into the specific heat. Okay, so the definitions of the true specific heat is like C equivalent to Q over M delta theta. Okay, Q, C is the specific heat. Okay, Q is the quantity of energy, M is mass, and delta T is the change in temperature, change in temperature. Okay, again, I want to highlight that change in temperature in this case, okay, regardless of the situation, regardless of the scale, either it's in Celsius or in Kelvin, okay, just two scales, not Fahrenheit, right? But obviously not Fahrenheit, just two scales involving Celsius or Fahrenheit, Celsius or Kelvin, regardless of that, okay, you need to know the calculations, or you need to know the difference between temperature, the difference between the value of temperature. Okay, that means temperature final minus temperature initial. Okay, so regardless of the scales, because I have proved that TC, if you want to convert it to Kelvin, okay, TC is equivalent to TK is TC plus 273 degree Celsius. If you want to convert it to Kelvin, you just need to add with 273 Kelvin. Okay, so with that, you can get, if let's say you want to add 20 to 270. So 20 degrees Celsius is equivalent to 293 Kelvin. 293 Kelvin. So, the difference between one final temperature of Kelvin and one initial temperature of Kelvin will be equals to a final temperature of Celsius and the initial temperature of Celsius if we minus it. Okay, so the delta here, don't bother about Kelvin or Celsius. You just need to know that look at the given appendix. Okay, look at the given appendix. In the appendix give you J, kg, K, you can put delta K. Okay, or J, kg, the C, you can put delta C. Okay, don't bother much. Okay, these are the examples of the specific heat at the atmospheric pressure. Okay, with the some fluid and also solid. Okay, look at the specific heat. The unit for specific heat is J, joule per kg Kelvin. Okay, joule per kg Kelvin. That means, okay, whenever you do the calculations, if you tend to, let's say, given to you 50 degrees Celsius to 30 degrees Celsius, so you just multiply, you just minus it, so you will get delta theta equivalent to 20. Okay, but obviously this one is 20 Celsius. Okay, but here is Kelvin. Does it have the same value? The answer is yes. Okay, because this delta theta will also give you 20 Kelvin. So just put 20 Kelvin to the equations. Okay, right? And then if you look carefully, water will have a very large value of energy. Specific heat of the water is much more higher compared to a solid at the bottom part of the table. Okay, bottom part of the table, right? It takes about 4,000 joule of of energy, okay, to increase just 1 degree Celsius or 1 degree Kelvin of 1 kilogram substance. Okay, and if you look carefully at lead or gold perhaps, okay, or silver, just only need 200 or 100 something. Okay, so it took about, so you can say that the solids, okay, it's very easy to to get heated and very easy to get cold. Okay, it took not longer time, but not to water. Water, if you want to boil it, just look at your kitchen. Okay, if you want to boil it, it takes a lot of time and then the heat will preserve. Okay, after sometimes, and very hard to cool it down. Okay, not so hard. Okay, but it takes a longer time compared to solid or compared to. So you can look at this part. Okay, that's why we didn't use we use a pan that made from iron, for example. Okay, made from copper, for example. Okay, because this kind of material is very easy to get heated, and at the same time will cool down. Okay, will be cooled down at very a smaller time compared to fluids. Okay, compared to at the very top of the tables. Okay. Alright, so having a large value of specificity means that water can give off or take in large quantities of heat with little change in temperature. Okay, so today I want to highlight in terms of a calorimeter. Okay, what is a calorimeter? So a calorimeter is a lightweight, okay, insulated flask. Insulated flask. What does it mean by insulated flask? Okay, that means we have covered the flask. Okay, so no heat can be easily come in or come out. That containing water. So you know water. Okay, water. So you can have flask with water, but right now we covered the water. We covered the flask. Okay, we covered the flask so that it becomes a calorimeter. Okay, very easy to get calorimeter. Okay, you just need to have some flask, but you need to cover it. Okay, cover it so that no heat can come in or come out easily. Okay, when an object is put in, the object and the water comes to thermal equilibrium. If the mass on the flask can be ignored and the insulation keeps any heat from escaping, okay, okay, so what will happen? Number one is the final temperature of the object and the water will be equal. How come it can become equal? Because it have already achieved a thermal equilibrium. Okay, and the total energy of the system is conserved. Okay, so let me do some thoughts on the calorimeter. Okay, basically in the calorimeter, we take some metal. Okay, we take some metal, for example. Okay, let's say this is your calorimeter. Okay, I will show you some. Okay, this is your calorimeter, a flask with water. Let's say this one is covered with insulated. Okay, not a normal beaker, but this one is a calorimeter. Okay, this one is water. This one is insulated flask. Okay, this one is water and insulated flask. So this one have been covered. Okay, covered. So no heat will go in or go out easily. So you have a water. Let's say the water is in 25 degree Celsius. Okay, if you take one metal, okay, this one is metal, you heated the metal. Okay, so the metal will be heated at least until 80 degrees Celsius. For example, 80 degrees Celsius, this one is metal. Okay, in a metal at 80 degrees Celsius, what will happen if we take this metal, we put it inside here, and we close the lid, and we close the cover of the insulated flask, and then what will happen is at 80 degrees Celsius, mid 25 degrees Celsius, so that this water will influence some thermal contact. Okay, this water will influence some thermal contact between the water and also the metal, and then you can say after the thermal contact, okay, there is some heat changes. Okay, because there is some contact between the bodies. Okay, so heat changes will happen, and then you can see that this metal okay, the temperature of the metal will go down at some T, okay, will go down to some T, and this 25 degrees Celsius will comes to the value of T. So everything will be in the final temperature. Okay, so you will reach at one final temperature. So that temperature will be the temperature of the thermal equilibrium. Okay, so examples. Okay, suppose a block of mass M. Okay, this is mass M. Specific heat CB. Okay, and initial temperature TB is dropped into a calorimeter containing water. If the water has mass MW, CW, and the temperature is a TW, find the final temperature of the block and water. Okay, so right now we need to know that this metal will have QB. Okay, okay, we can say that the metal contain some energy with the value of QB, and the water is QW. Okay, QW and QB. That means the quantity of energy of the water, and QB is the quantity energy of the block. Okay, so QB and Q water. So this one is for block. This one is for water. Okay, so remember about the conservation of energy. Okay, so the quantity of energy of the block and the quantity of energy of the water, if you add it, will become zero. Okay, because of the conservation of energy. So you can put these things to the other sides, or you can just be that way. Okay, so this is the QB. That means mass of the block, and B. CB is the specific heat of the block. Okay, it comes from what? From what? Q equals to MC delta T. Remember, delta T is what? Delta T is T final minus T initial. Remember, okay, let's say, okay, the initial temperature uh of the water and the block. Okay, so TB is 80 degrees Celsius, while TW is 25 degrees Celsius. So T is the final temperature. Okay, T is the final temperature. So you need to put it here, right? So from here we can say that, right? So this one is MbCbT minus TB. How come T minus TB? Because this one is a T final and TB is the TE initial. Okay, plus with MW, M water, CW, C water. Okay, okay, that means specific heat of water. Okay, so the final temperature will be T and the initial temperature will be W. Okay, that equivalent to 0, right? So that's why we can get T, the final temperature, from this kind of equations. Okay, I would like to remind you, don't remember these things. Okay, but there's a lot of questions that a lot can be asked using the calorimeter, using this kind of situation. Okay, a lot of the situation will come to you in terms of calculations about calorimeter. Okay, so you can say that this is the quantity of the block and the quantity of the energy of the water. Okay, quantity energy of the block comes to quantity energy of the water, then you can have some that will be equivalent to 0. So from that we can find the final temperature of the combined block and water. Okay, these are some examples of the block and water. Okay, for example, suppose a 550 gram of water. So this one is what? MW at a 32 degrees Celsius. So this is TW. Pour into a 210 gram aluminium. So this one is the MB with an initial temperature 15 Celsius. This one is TB. Find the final temperature of the system assuming no heat is exchanged. Okay, the words are no heat is exchanged. That means you can have QB plus QW equals to 0. This is okay, you need to know that QB plus QW will be equivalent to 0. That means no heat is exchanged, no heat is, so that meaning that they are using calorimeter. Okay, so you can use this equation in order to find the value of 31 degree. The final answer is 31 degree Celsius. Okay, so let's look at another examples. 0.5 kilogram. I want to highlight it. In terms of mass, everything must be done in the SI unit. Okay, so this one is 210 gram. So you need to convert it, okay, to kilogram. Okay, 550 gram. You need to convert it to kilogram. Okay, so everything must be done in SI unit. Right. Okay, let's look at another example. Okay, a 0.5 kilogram block of metal with an initial temperature of 55 degrees Celsius. So this one is the initial temperature of the block, TB. Okay, it's dropped into a container holding 1.1 kilogram. So this one is MW at 20 degrees. So this one is TW. Okay, if the final temperature of the block water system, this one is what? T. This one is T. What is specific heat of the metal? So the question asks you to find, okay, what is the C? Okay, CB. Assume that the container can be ignored. Assume the container can be ignored and no heat is exchanged. Again, these are the key points. No heat is exchanged. That means you can use QB plus QW equals to 0. Sometimes there may be somebody will emphasize on QB equivalent to negative QW. Can also be done. The same thing. Okay, QB plus QW equals to 0, or you can write down as QB equals to negative QW. Or else you want to find QW equals to negative QB. Also can be done. Okay, it's up to you. Okay, because in the final answer will only get the same value. Right? So these are the how they did. So the Q block again. So these are the final temperature, that is 21.4. Okay, so we want to find what is the CB over here. Okay, and from the calculations you will get CB is 390 joule kg K. Okay, kg K. Look at the term used in the CW. CW is 4186 joule per kg dot K. Per kg dot K, that means the temperature you need to use is in Kelvin. But if you look carefully, okay, this person doesn't use Kelvin, but they use only Celsius. Does it okay? Yes. Again, I'm telling you, it's just a delta. It's just a difference in temperature. The delta in Celsius will be equals to delta in Kelvin. The same thing. Okay? Because it's proportional. Right? So don't bother much. You just add. You just minus with Celsius, but you put a Kelvin. You put K on the value of because we can multiply and we can cancel out with the CW with the units of CW. So the final answer is 390 joule kg kg Kelvin. All right. So let's look at one final subtopic for this chapter, which is conduction, convections, and radiations. Okay, look at what they have. What is the meaning of conduction, convection, and radiations? Okay, the conduction, convection, and radiations are three ways that heat can be exchanged. So this is how the heat can be exchanged through conduction, convection, and radiations. Okay, so first is conduction. Okay, the conduction is the flow of heat directly through a physical material. Okay, flow of heat, okay, directly through a physical material. That means in conduction you need to do some contact. Okay, you need to contact between the bodies. So the conduction is the flow of heat from, okay, if you want to conduct heat from T1 to T2, okay, you can it can be transferred with using this kind of rod. Okay, all right. So this one we happens to see that if you have one bodies, okay, let's say this is uh, object number one and object number two. This is temperature one and temperature two. Okay, you can see between if there are two different in temperature, so the heat can flow. Okay, the heat can flow from two different temperature when there is a contact. So these are the connector. This connector contain a length, some length, and also area. Okay, if happens to see that this is kind of rod. Okay, you can see here the area is if you look at the on the side, or if you look at the side, okay, this is like a rod. It's something like rod, yeah, with some area of circles. When you multiply with L, you can get some rod. Multiply with the length. So it contact between T1 and also T2. So you can see there will be heat flows between the body number one and also body number two. Okay, look at how they did in experimentally. Okay, maybe you didn't need to use it to look at the experimental, but you can easily imagine how they did this experiment. Okay, is it found that the amount of heat Q that flows through a rod, okay, it is found that the amount of heat Q flows through a rod. Okay, why it flows through a rod? Because there is some thermal contact, and therefore the heat can flow from one side to another side. Okay, so the rod, okay, what happens when the heat flows to the rod? It increases proportionally to the cross-sectional area A, and increase proportionally. This one happened. This one is just a observation, okay, and also findings from the experimental. Okay, so it happens that, okay, the heat flows can increase proportionally to the cross-sectional area. That means the larger the area, more heat can flow. Right, larger the area, heat can flow more. The increase proportionally to the temperature difference from one end to the other, to the other. That means if there is a lot of difference in temperature, that means between 5 to 3 and 50 to 10, okay, this one is only 2. This one is 40. Okay, so 40, the heat can flow more on the big difference in margin in difference in temperature. Okay, and the heat can also increase steadily with time. Oh, okay, then it also involve time. Okay, that means you can also involve time in this heat transfer. Okay, and but it will decrease with the length of the rod. Yes, the length. What happens is if it is longer, then the heat will not be traveled in much time because it races against time. Okay, so decrease the longer the rod. Okay, the heat flows will be drop. Longer the rod, okay, the heat flow will be decreased. When after we combine, we can have some heat flow by conduction. Okay, heat flow by conduction. Q is equivalent to K, so, the thermal conductivity. Okay, the thermal conductivity is the some appendix. Sorry, some values taken from every material. Okay, A is the area, delta T is the difference in temperature, L is the length of the rod, and T is the time. So we take everything into consideration. So K QA delta T over L times T. And where K is just some random value. K is random value based on the material. Okay, so these are typical thermal conductivities. So that means these are some K value. Okay, what is K value? Okay, then it looks differently into a certain substance. For example, if you look at the in the top part, you can see this one is like a solid. Okay, and decrease to fluid. So the value is increasing when it becomes solid. Okay, silver has a better thermal conductivity compared to glass, for example. So, okay, the thermal conductivity that happens. That means if you have one thing, okay, object number one and object number two, okay, if you want to get a better thermal conductivities, so you need to put everything on the upper part of the table. Okay, just put a copper, a gold, aluminium, so it will transfer a better transfer of heat to the other part. We compare to if you put air, if you put wood, if you put wool in between the object number one and object number two, we compare to on the upper part of the tables, so it will be lesser. Okay, so substance with high thermal conductivities are good conductors. So that these are some things we learn, that a substance, okay, that have high thermal conductivities, you will tend to have a good conductors. Okay, so again, if you want to know how good is your the substance in terms of electricity, so you can apply. Okay, you can refer to this thermal conductivities table, because the better the conductivity, the thermal conductivities value, it will give you a better conductors. Okay, but the better conductors of heat. Okay, I want to emphasize on conductors of heat, not electricity. Okay, those with low thermal conductivities are good insulators. So if the question asks you, okay, if that said they are giving some cases, okay, case study to understand which material or which substance can be good in terms of insulators or conductors. Okay, so you need to remember about the some thermal conductivities. Okay, refer to the thermal conductivity value. Okay, if the value is greater, that means it's a good conductor. Okay, let's look at the examples. One of the windows in the house has the shape of square 1 meters on the side, 1 meter times 1 meters. Okay, the glass in the window is 0.5 centimeter thick. Okay, and how much heat is lost through this window in one day if the temperature in the house is 21 degrees Celsius and the temperature of the outside is 0 degrees Celsius. Okay, it's obviously this is some kind of what happens on our house. Okay, let's say this one maybe not 0 degrees Celsius. Outside, maybe when you live in the overseas, okay, um, and the outside, let's say the outside is 0 degrees Celsius, and uh, in your house, the temperature is 21 degrees Celsius in average. Okay, so there is some window is made from glass. Okay, made from glass, and of course, if you can see, or in our theory, okay, this is one body. Yeah, that means one temperature at side one, and this is another temperature. So there is some two different temperature that not equal. Okay, so with the glass as a separator, the glass will become a thermal a conductor to the heat. So the glass will transferring some heat. Okay, how they transfer is based on the thermal conductivity value. So if you referring to glass, the thermal conductivity is 0.84. It's not a good conductor, but it's a good insulator. So that's why we put glass, okay, in between the house. Okay, so on the outside, okay, the temperature is 0, and inside the temperature is 21 degree Celsius. And then of course you can apply these equations. Okay, Q equals to Ka delta T over L times T. T is temperature, delta T is the T is time, delta T is the temperature. So 0.84 watt per meter Kelvin, times 1, the area, okay, 1 meter square, times with 21 K Kelvin, the delta in Kelvin, okay, and over 0.005 meters, because L is the length. In this case, L is the thickness of the window. So you can get 3,500 T, because it didn't state any time inside that. Okay, so you just let the answers with T. Okay, but the question now is, okay, 1 day. Okay, 1 day is equivalent to what? Okay, 1 day is equivalent to 24 hours, and 24 hours is based on 24 times 60, so you will get 86,400 times 60 times 60. Okay, because 1 minute equivalent to 60 seconds. Okay, so what? Okay, remember, if you want to multiply what is what, yeah, and joule per second, remember what is 3,500? What is equivalent to 3,500 joule per second? So we need to cancel out time in seconds. So it's S and S, so left just only joule. So the answer is 3 times 10 power of 8 joules. Okay. Suppose all the dimensions of the window height, width, thickness are double. If everything else remains the same, by what factor does the heat flow change? Okay, so using the same value. So right now, okay, they have double everything. Okay, for example, the area, if they double the area, so you can find 4 times area. Because this one becomes double, 2 and 2. So 2 plus 2 is 4, 4. 4. So already 4 times with the area. Okay. So the area is 1 meter per second. Okay. Delta T. Okay. Just everything doesn't state here. So delta T is not double. Okay. But 2L is double. Okay. So you will get later on that the value will be 2 times the heat. Okay. 2 times the heat. So we can um, uh, factorize 2 outside, and we will still get this one as Q. So 2 times Q. So that will be the factor. Okay, look at another examples here. Okay, two 0.525 meters rod, one lead and the other is copper, okay, are connected between metal plates held at 2 degrees Celsius and 106 degrees Celsius. Okay, 1 and 2. 100 and also 2 degrees. The rods have a square cross-sectional area. Okay, cross a square. Rods have a square cross-section, 1.5 centimeters on the side. That means 1.5 times 1.5. Okay, how much heat flows through the 2 rods in 1 second? Assume that no heat is exchanged between the rods and the surrounding, except at the ends. Okay, it's a very good question in order for you to understand the thermal conductivities. Okay, there is some difference in temperature, obviously 2 and 106. So you can see we put lead and also copper. Okay, there are two substances that have a different thermal conductivity value. Okay, first we need to calculate from lead rod. So Q Ka delta T over L times T. So referring to this table, okay, 34.3 for the lead. Okay, 34.3 for the lead. Okay, you times with 0.015 meters square because it's a square. So you multiply with its own. It's 104 Kelvin. Okay, because 106 minus 2, so you will get 104. And 0.525 meters. Okay, the length is 0.525 meters times 1 second. So you will get 1.53 joule. Okay, and then if you look, you took a copper, see, so referring to the copper, the thermal conductivity value is 395. Okay, much more different compared to lead. Okay, 395. So follow the same value. So you will get 17.6 joule. Okay, so the question now is how much heat flows through the 2 rods? How much heat flows through the 2 rods? So you can add everything, 1.53 plus with 17.6, you will get 19.1 joule. Okay, 19.1 joule. The total heat flows. Okay, all right. So that is the conduction through a thermal conductivity. That means you need to do some you need to connect between the two bodies between using some thermal conductivities. Okay, some material that have a different thermal conductivities. Okay, let's look at what is convection is all about. Okay, the convection is the flow of fluid due to a difference in temperature. Again, they highlighted about difference in temperature. Conduction also have difference in temperature because that is the key part of the heat flows. Because if the heat wants to flow, there must be some difference in temperature. All else it cannot flow. Okay, because that is the zeroth law of thermodynamics. Okay, must have difference in temperature. Okay, flow of fluid due to a difference in temperature, such as warm air rising, the fluid carries the heat with it as it moves. So it happens in the sea breeze and the land breeze. Basically, when we comes to we go to the beach, okay, or on the daytime, okay, we can feel a sea that breeze, okay, because compared to land and water, okay, the water will have a greater uh, a greater greater specific heat during daytime, and the land will get warmer easily compared to water. Okay, the land will be warmer compared to water. Is a uh, so when the land get warmer, okay, compared to water, so the warm air will goes up, and then because it lost its density, and the sea breeze will flow from here to, okay, in order to replace, okay, to replace the warmer the lands, okay, to replace back the breeze on the land that happens to get on the top sides of the atmospheric. So the sea breeze will flow from the air to the land. Okay, when compared to the night time, okay, because the heat from the water, okay, in the daytime, okay, is giving more warmer. So the heat from the water will goes up first, and then the land it will replace by the warmer land breeze, okay, coming from the land. So you can feel a land breeze. Okay, a land breeze. That means uh, uh, breeze from the land. Okay, that replacing the warmer part of the waters that happens to be on the top sides of the atmospheric. So that's how the convection and the flows of fluid have been replacing. Okay, so the land get warmer, okay, the sea breeze, okay, will replace it, and when the on the night time, um, the sea breeze, okay, the land breeze will flow from land to the sea, okay, because the sea happens to have a higher conductivity, heat capacity, so it will be warmer in longer time, right? And then it will be goes up because the heat can still there. The heat will goes up, okay, because it lost its density, and the land breeze will flows from the land to sea. In daytime, from sea to land, okay, by replacing the hot breeze. Okay, so that's how the convection. Okay, it's just this the convection in Malay we call it a perolakan. Okay, perolakan. Okay, and then afterwards you can see the radiations. Okay, objects give off energy in the form of radiations. For example, electromagnetic wave. Okay, you cannot see the electromagnetic wave, but we can feel it. Okay, so this happens when you have freeze temperature, for example, electromagnetic wave, infrared, visible light, ultraviolet. Okay, everything in the electromagnetic wave, for example, infrared, visible light, and ultraviolet. Okay, so the unlike conduction and convection, okay, the heat can be transported through a vacuum. So that's how we can feel the heat comes from sun. Okay, although it travels a lot of time, but we can still feel the hot from the sun through some vacuum. So that means no contact, no replacing with the convection, no convections, how they replace the warmer breeze or whatsoever, but we can still feel the heat. So through the vacuum, the heat can also travel if there is some difference in temperatures. Okay, so objects that are hot enough will glow, first red, then yellow, white, and also becoming blue. Objects at body temperature radiates in the infrared and can be seen with a night vision binoculars. So we cannot see. So that's why the snake, for example, okay, is hunting its prey using is hunting its victim using the visions of some things like this one, infrared. Okay, the snake can see heat from its victims so that it can hunt in the on the night. Okay, so that's why uh, the visions, you can say that the object's body temperature will radiate accordingly to the um, to the colors. Okay, objects that are hot enough will glow. Okay, so they will glow. If you look at the visions in the night color visions, you can see on our side. Okay, if we tend to get warmer on the several certain sides, okay, it will get hotter. You can see the change in colors, the different change in colors to our sides. Okay, so all object, this one is what we call as radiations. So now the heat conductions based on number one, conductions, number two, convection, and number three, radiation. Okay, so you need to know about conductions. Q equals to Ka delta L over delta T over L times T. Ka delta T over L times T. Okay, where the convection you need to know about land breeze or sea breeze, and radiation about EM wave. Okay, the amount of energy radiated by an object due to its temperature is proportional to its surface area and also the fourth power of its temperature. Okay, so this one is some summaries. Okay, so I think we take a break for a few minutes and we will continue later. Okay, so let's continue. Okay, so this is the phases and changes. Okay, phases and changes. So you can see some changes. So in this part, okay, we will learn about solid and elastic deformations. We have already covered these things, and today we will touch on the latent heats and also the phase change and the energy conservation. Right? So let's look at what is the solids and the elastic deformations. Okay, we should skip this one, but this is just some uh, things that we have learned about solid deformation, which is the Young modulus for the linear, the bulk modulus, sorry, the shear modulus for the area, and also okay, the bulk modulus for the volume. Okay, and also the stress and strain. Right. So today, okay, I want to highlight on the latent heats. Okay, the parts where we learn about latent heats. When two phases coexist, okay, two phases coexist, the temperature remains the same even if a small amount of heat is added. Alright, two phases, fasa, okay, dua fasa exist, temperature yang sama, okay, and small amount of heat is added. Okay, so there's some heat we add, but no change in temperature. Ini ayat yang okay, yang tepat, no change in temperature. Delta T equals to 0. Right? Cool. So in this part, okay, in this part, instead of raising the temperature, the heat goes into changing the phase of the material. For example, melting ice. Okay. So we add some heat into the system, but the temperature didn't goes up or goes down. Okay. In fact, the heat is only required to change the phase of the material. Okay. Menukar fasa. Okay. Tukar fasa dia. Contoh dia, melting ice. Okay. Peleburan ais. Okay, ataupun ais, cairan ais. Okay. The heat required only to convert from one phase to another. So that is what we call as latent heat. Okay. Heat is added to the system, but the temperature remain the same. Okay. Remember, no change in temperature, but in fact, it's just the change of the phase of the material. Okay, the phase of the material. So in this case, you need to look at where is the when there is no change in temperature, so that will be where is the latent heat will cause. Okay, so what is latent heat? The latent heat is the heat that must be added or removed from 1 kilogram of substance to convert it from one phase to another. Okay, the heat that must be added to remove from added or to remove from 1 kilogram of substance to convert it from one phase to another. Okay, it's just to change the phase. Okay, during the conversion process, the temperature of the systems will remain constant. Ini ayat paling penting sekali. Okay, the temperature will remain the same. So because of that, the definitions of the latent heat, so we can write down this equation as M times L. That means M is the mass and L is the latent heat. Okay, latent heat, the unit is joule per kg. Joule per kg. Okay, so in latent heat, we have a latent heat of fusion, latent heat of vaporization, and another one is latent heat of sublimation. Normally, we will always use latent heat of fusion and latent heat of vaporization. Okay, where is latent heat fusion and vaporization? We will look later. Okay, but what happened to the latent heat of sublimation? Okay, if you look carefully, what is latent heat fusion? Heat needed to go from solid to liquid. Okay, from solid to liquid. What happens when from liquid to gas? So latent heat of vaporization. This is the keyword, vapor. Okay, vapor means water vapor. Okay, dalam bentuk wap air. So from liquid to gas. And what happens to the latent heat of sublimation? From solid directly to gas. Pemejal luapan. Dalam sains, we call it as pemejal luapan. To go from solid to gas straight away. It skips liquid part. Okay, so this latent heat of sublimation. So we will depends on the situation either to use latent heat of fusion or vaporization. This from this table you can see a latent heat of various materials from water until oxygen. Okay, in this case, okay, every value will have its own fusion and vaporization. So we depending on where we want to use a latent heat of fusion and vaporization, depending on the liquid itself. Okay, right. So need to see the where is the specific latent heat of fusion and vaporization. So these are some uh, heat graph of temperature against heat. Okay, this is the graph of temperature against heat. We can see some uh, uh, increase in temperature that also involving heat added. Okay, for example, at negative 20 degrees Celsius, which is here. Okay, at negative 20 degrees Celsius. So at this point, we can say that, okay, at this point, the water is in ice form. Okay, is in ice phase. Okay, dia dalam bentuk ice. And ice is solid. Solid. At negative 20. And because water at 0 degree is only becomes a freezing point. 10. Okay, at 0 degree, the water becomes freezing point. So obviously before that, it becomes solid. Okay, so in here, from negative 20 to 0, so you have already add some Q, which is what? MC delta T, because there is a change in temperature. How change in temperature? From negative 20 to 0. From negative 20 to 0. Right? So what happened is, okay, if you look at from point A to point B here, from point A to point B, you can see that there is no change in temperature. At 0 degrees Celsius, no change in temperature. So this is where we use latent heat of fusion. This is where we add heat to the system in order to change the phase. From what? From what? From solid to liquid. So that's why we use LF, latent heat of fusion. That means in here we will use Q equals to ML. Right? And then at point B to point C, okay, so at point B, okay, the water now becomes liquid. Okay, so becomes liquid at least until it reach 100 degree Celsius. So at this point, we will use Q equals to MC delta theta because there is some difference in temperature. Okay, difference in temperature. So we will use MC delta theta in order to calculate heat. And then at point C to point D is where we can use a latent heat of vaporization. Latent heat of vaporization, which means we want to convert it from liquid phase to gas phase. From liquid phase to gas phase. So again, Q equals to ml. But this one is mlf, this one is mlv. Okay, so that's how you can calculate all the energy needed from point of negative 20 degrees Celsius to 120 degrees. So I would like to highlight on this. Let's say the final temperature of the steam is negative 20. That means you need to add another Q over here. Q equals to MC delta T. Because there is some change from 100 to 120 degrees. So these are the some process involving heat added to the water system from solid part becoming water vapor or becoming gas phase. Okay. So let's say if the question asks you calculate the heat required to raise the temperature of 0.55 kilogram of ice. Okay, remember 0.55 kilogram of ice from negative 20 degrees Celsius to water at 20 degrees Celsius. Okay, so this is negative 20, negative 20. So there are three parts, which first is the MC theta. Okay, Q equals to MC delta T. Look at how they use MC delta T. So M is 0.55 using the same value. C is the specific heat of not water, of ice. Okay, because at that point, ice and water is two different phase, two different phase. We cannot say that ice is water, water is ice. So water have its own specific heat, while ice is also have its own specific heat. So 2090, okay, by referring to our table, okay, and then delta T is here, 20 degree. So in the end, the value is 23 kilojoule, right? On the second part is because okay, if negative 20 to 0 from 0 to 20, so you took about at least three processes. Okay, three processes at this point, at this point, at this point. Okay, this point to this point, QMC delta T. This one is Q equals to ML, and this one is Q equals to MC delta T again. Okay, so at the latent, at the point B to point C, you can say that there is some latent heat of fusion. So you need to use 0.55 and then times with latent heat of fusion of what? 33.5. Okay, 33.5 is water. Okay, 33.5 latent heat of fusions of water. That equivalent to 18,400 joule. Sorry, 184,000, 184 kilo joule. And in the end, okay, we will calculate back, okay, the Q3. So this one is Q1, this one is Q2, and this one is Q3. So MC water, look at how they did. 0.55 is the mass, okay, but at that time, we have already turning into water. So we use seawater. We use seawater times with 20, then you will get 46 kilo joule. So the answer is the total heat, you add everything to get 253 kilojoule. Okay, kilojoule. Okay, so let's look at one example here, right? To make steam, you added 5.6 10 power of 5 joule of heat to 0.22 kilogram of water. Okay, so we are saying that this one is a liquid. Okay, this one is gas. At an initial temperature of 50 degrees Celsius. Ini awal-awal. And find the final temperature of the steam. So from 50 to 100, because it's water, and water boils at 100 degrees Celsius. So this one to this, you need to apply some Q equals to MC delta T. But this one is using sea water. Okay, sea water. After that, okay, we will apply some Q equals to ML, latent heat of vaporizations. Okay, refer to our table, latent heat of vaporizations. There should be VLV over here, latent heat of vaporizations. Okay, and then from Q3, okay, Q3, So you calculated back, and then you the total heat have already given 5.6 10 power of negative 5 10 power of 5 joules. So you can minus Q1 and Q2 in order to get Q3. And after you get Q3, you apply to this part and using C steam, C steam, not C water. So C steam 2010 joule per kg per Celsius. So you can get 38 degree Celsius. So the delta theta will be 38 degree Celsius. So we can say that, okay, from here, the delta theta will be 38 degrees Celsius. All right. So that means the final temperature is 138 degrees Celsius. Okay. So that's why it's very important to understand the concepts of uh, Q equals to MC delta theta and Q equals to ML. So where is you should use to Q equals to ML during the phase change. What is the phase change? So the heat required to change from one phase to another phase without changing the temperature. So that is the key point. Without changing any temperature, we can have the phase change. Alright, so let's look at the phase change and the some energy conservation. Solving problems involving phase change is similar to solving problems involving heat transfer, except that the latent heat must be included as well. Okay. So before this, we have learned about QB plus QW equals to 0. In this case, we need to apply the same thing, but right now we need to add a latent heat as well. Okay, because it involves the phase change. Okay. Let's say in the situation of 0.042 kilogram ice cube at negative 10 degrees Celsius is placed in a cup containing 0.35 kilogram of water at 0 degrees Celsius. Okay. Find the mass of ice in the system when the equilibrium temperature is 0 degrees Celsius is reached. The question asks you, find the mass of ice in the system when the equilibrium temperature is 0 degree Celsius is reached. So that means you can say that this one is ice at negative 10. This one is water at 0 degree Celsius. So ice and water is two different phases. Ice is a solid where water is a liquid. Okay, so in this case, negative 10 to 0 is where it involves change in temperature. And at the same time, it also involves the change in phase. So that's why we need to do it carefully. Okay, so this is how they did. Okay, first, heat gained by the ice. Okay, heat gained by the ice through some calculation. MC ice delta T. Okay, M is 0.04. You take the mass of ice, okay, times with the CW of ice, 2090, and also the change in temperature, negative 0 minus with negative 10. Okay, this one 0 minus negative 10. So it becomes 10. So the answer is 878 joule. So heat gained by the ice is equivalent to heat lost by the water. Okay, because that is how we assume about heat, quantity of heat. That means heat can be transferred. It cannot be demolished. It can be transferred to another form. That means heat gained by the ice. Okay, ice dapat heat. Dan sebenarnya heat itu dapat daripada siapa? Heat loss daripada air. Heat loss from the water. So it's equivalent to 878 joule. Now, the water is at 0 degrees Celsius. Okay, water is 0 degrees Celsius. Removing heat from it does not lower the temperature again. So maksud bila tidak menurunkan dia punya temperature, so that's why at that particular time, okay, it remove the heat, converts into some ice into water. So that part, that particular part, okay, heat lost by the water equals to mLF. So we can assume that 878 joule will be equals to mLV. Sorry, LF, the heat of fusion. And that particular time, we can have mass that equivalent to 0.00262 kilogram. Because in this case, we have already have LF, we're referring to the table, and we need to calculate to get mass. And when we have mass, we can see that from ice, 0.0420 kilogram, it becomes water at 0.00262 kilogram. So when you add up the value, the final amount of ice, so it will become 0.042 plus with 0.00262. The answer is 0.0446 kilogram. You need to do it carefully because it involves a lot of decimal point. Because at this point, okay, the value is not is very small compared to the one that we did, because it just involved a little bit of heat. Okay, it just involved heat and we cannot contain a lot of kilogram. Okay, so 0.042 kilogram, the ice from the ice, the heat gained by the ice. Okay, that is the original mass. And you add with some ice, because the question asks you about find the mass of ice in the system when the equilibrium temperature is reached. Okay, find the mass. So the mass is 0.0446. Okay, there's some added in the value of mass. Okay, so let's look at this one particular example. A large punch bowl holds a 3.95 kilogram of lemonade, which is essentially just water. Okay, and water, that means liquid, at 20 degrees Celsius. A 0.045 kilogram ice cube at 0 degrees Celsius is placed in the lemonade. Okay, you take ice, some 0.045 kilogram ice, you put inside the lemonade. What is the final temperature of the system, and how much ice remains when the system reaches equilibrium? Ignore any heat exchange with the bowl or the surroundings. So we can say that no heat flows in, or no heat goes in or goes out. It just happened to be on this bowl only. It's between ice and water, ice and lemonade. Okay. So you can see here, the initial condition 0 degrees Celsius, 20 degrees Celsius, 20 degree lemonade, 0 degrees ice. Okay, so first we need to calculate the heat gained by the ice. Okay, heat gained by the ice between 20 degree to 0. So in here, okay, so 3.95 kilogram of ice, 3.95. Sorry, bowls. Bowl holds lemonade, 3.95 lemonade. M water, C water, delta T. Okay, because it's come from from water. Water have its own Q, and then we need to add ice. We need to know ice between heat of water and also heat of ice and water. Okay, so M water, C water, delta T. So 3.95, 4186, 20 degree, because it's between 20 to 0. Okay, 20 to 0. So 0 minus with 20. So you will get negative 20 or 20. So you will get 3.31 times 10 power of 5 joule. And then between ice and water, so you can multiply with using latent heat of fusion, because ice becoming water. So latent heat of fusion using ice, mass of ice times with the latent heat of fusions of the water. So you will get 1.51 10 power of 4 joule. See, determine the amount of heat that is left. The amount of heat that is left. So that means Q water minus with Q ice. Okay. In this case, you will get 3.16 10 power of 5 joule. Okay. So the question now, okay, when the final temperature of the system, how much ice remains? How much ice is remain? So using, because right now we can see that water and ice have been uh, added together. So you add m water and m ice, which is the mass of water and mass of ice, using the seawater and delta T in order to get the final temperature, because final temperature, and lastly we calculated the final, the remaining ice. Okay. Okay, so the value will be here 3.16 10 power of 5, the remaining part. Okay, and then 3.95 plus with 0.054 times with the seawater, and then you will get to see that the delta T, the final temperature, will be 18.9 Celsius. 18.9 Celsius, right? From 0 to 20 degree, so it reached until 18.9 degree Celsius as a final temperature. So the remaining ice is here. The final temperature, final heat is equivalent to 3.16 10 power of 5 joule. Okay. All right. So in summary, we should look at the system of the latent heat, okay, in which we learn about latent heat, okay, latent heat of fusion, latent heat of vaporization. It also involved with the MC theta. So remember, it comes together with the specific heat, not just a specific heat, MC delta theta, delta T. It also involves latent, when it comes to the phase change, it also involves latent heat of fusion and vaporization. And sometimes, sometimes they will highlight about latent heat of sublimation. Okay, but be careful on that. Okay, be careful on that. Okay, all right. So there is a summary of chapter. Okay, latent heat is the amount of heat required to transform from one phase to another. Okay, latent heat of fusion, either melting or freezing point. Okay, latent heat of vaporization is either vaporizing or condensing. Okay, condensing means from gas to liquid. And latent heat of sublimation or condensation, directly between gas and solid. From solid, directly becoming gas, or gas becoming solid. When heat is exchanged within the system isolated from its surrounding, the energy of system is conserved. Remember, Q delta Q, QB plus QW equals to 0. But right now, you need to add Q of the phase change. Okay, then again, all right, that will be the end of this chapter. Okay. Is there any questions? Ada soalan? Okay, next week will be our last topic, involving thermodynamics. Okay, involving the last topic will be the thermodynamics. Okay, so please please look at the pre-recorded videos before you come to the class, and we will discuss it thoroughly during our classes. Okay? Ada soalan?